Okay, so one of the things that pops up when you're dealing with these purely imaginary numbers is what happens when you raise the number I to a power. So remember, I is the square root of -1. So when you square it, you should get -1, and you do. I squared is always -1. We've already covered that in an earlier video. However, when you start raising it to powers bigger than that, some interesting things start to happen. So let's look at what I cubed is. I cubed means I times I times I. Now, if you look at that, within this group of i's, I have an I squared, which again, we found out is -1, and then I have this I. So this is -1 times the square root of -1, but I don't write it that way because it looks confusing. So this is just -I. Whenever you raise I to the third power, you get -I, and there's no power on it. If I look at I to the fourth, it's I. If I look at the first two and the last two, those are both I squares. So that's -1 times -1, which is +1. So I raise I to the fourth power, and I don't even have an I anymore. It's just plain old 1. Now, once you go to bigger powers, I to the fifth, I could actually write as I to the fourth times I, and this I to the fourth is just 1. So that's just plain I again. I to the sixth, I to the fourth times I squared. So that's 1 times -1. I to the seventh, same idea. This is 1, this is -I. I to the eighth, I to the fourth times I to the fourth. 1 times 1. 1. So if you look at the pattern of things that we've got here, we have an I, -1, -I, 1, and then it repeats, I, -1, -I, 1. So basically this pattern of power of i's runs in a 4-cycle pattern. It's basically the same 4 things over and over again. So one of those very math teachery things to do, and it doesn't pop up much in Algebra 2, but it pops up in later math, is if you raise I to something like the 53rd power. Now look, I could write 53 i's out and then circle groups of 4 of them and find what it is, but that just seems overbearing. So here's what I'm going to do. I'm interested in figuring out, taking all the groups of I to the fourth I have, which are 1, and sort of like just setting them aside, because that's just going to be times 1 times 1 times 1 times 1, however many times we have it. So what I'm going to do is I'm going to take this 53, and I'm going to divide it by 4. Now, the reason I do that is that gives me the number of groups of these 4 i's that I have. So let's see. 4 goes into 5 one time. 1 times 4 is 4. Subtract 1. Bring down the 3. I know it's been a long time since some of you have seen long division. 4 goes into 13 3 times. 3 times 4 is 12. Subtract, and you have 1. So that means I have 13 groups of I to the fourth. But that's just that's just 1 times itself 13 times, which is still 1. This is not the number I'm interested in. The number I'm interested in is how many i's I have left over in the end. And that is this number. So really this I to the 53, 52 of those go into giving me 1 times 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 1. And then at the end, I have 1 lone I. So this is going to be I to the first, which is I. So essentially, if you have I to some big power, you take the power, you divide it by 4, you disregard the quotient, because that's just a bunch of 1s times each other, and you basically say the remainder is the number of i's I have left. And then you look at your pattern to see what the actual value is. So in the end, whenever you have I to a power, you should be able to simplify it where there is no power on an I at all.